Now we've seen some nice properties of limits and some theorems, sandwich theorem, theorem 4, but there's some limits that are going to come up enough that we'd love to not have to keep arguing over and over again what their limits are. So what this textbook has done is gathered together some common limits that in the stuff we're going to be doing, these will come up quite a bit. And so you don't have to re-argue them. When these come up, you can just say the limit is this by theorem 5. This will be the only theorem that you really have to quote by number. And so let's take a look. That first limit we just looked at, natural log of n over n, you could prove that by L'Hopital's rule, but now you don't have to anymore. You can just say it's 0 by theorem 5. The next one, nth root of n, that's an indeterminate form. The root is trying to make that come down to 1. The base is trying to make it go up to infinity. So you could do that. You could switch over to the function, write it as an exponent, do that e to the natural log business we looked at. But it would take some time. Now we're just going to use this as a fact. That limit is 1 by theorem 5. The next one there, the nth root of x, that guy is not as indeterminate really as this first one. X is some fixed number. That may be a little confusing at first. We're so used to x as a variable. But in the future, when we look at what are called power series, n is the variable in the sum, and x is some fixed number that we just haven't specified. So think of x as a constant. So maybe that's the nth root of 7. So as you take higher and higher roots of 7, that's going to go down to 1. And that's true for all x greater than 0. The reason they say that is if x is less than 0, depending on the root, every other root doesn't exist. So it doesn't really make sense as a sequence. But you can just quote theorem 5 on that. The next one, we'll see this quite a bit, some constant to the n. Now you might think that we don't need that as a theorem because we know that if the base is less than 1, that is exponential decay. And really for a positive base, you could make that argument that it's clearly 0. But what's less obvious, notice that this says this is true for all x less than 1 in absolute value. So remember, that means from -1 to 1. So even for negative bases, which you didn't look at negative bases in Calc 1 because that same problem I talked about before, it's undefined a whole bunch. But when the exponent is a natural number, that thing is defined. And so any base, even if it's negative, between -1 and 1, that limit's going to exist and it's going to go to 0. This next one here with the 1 plus x over n to the n, to be honest, that's not something that in the work we do comes up all that often, but it's an important limit. Because if you look at this, this tells us a definition for the function e to the x. And right now, we haven't ever really seen anything like this as a function equal to a limit. So this guy is nice, but I don't think it's going to come up for us very often, but it's a nice limit to understand. And then the last one is actually one that is quite hard to prove because now we've got factorials. Much like -1 to the n, we haven't seen factorials much in calculus because factorials are only defined on the natural numbers, right? So as a function, factorial doesn't make sense. It's not differentiable, it's not integrable. But this limit's giving us a new piece of information here. Remember earlier we talked about growth rates. So what is this? This is an exponential on top of a factorial. And it's telling us that out at infinity that ratio heads to 0. So what that's telling us is those factorials grow much, much faster than exponentials. So if you think about all the stuff we've seen, logarithms very slow, polynomials or power functions grow faster, and then exponentials were the fastest thing we knew. Well, now we have this new even faster thing, and that's factorials. So factorials grow faster than exponentials is really what that last statement is saying. So let's look at an example of using these properties. So say we were looking at the limit as n goes to infinity of the nth root of 8n cubed. Now that is not any one of those things in that list, but it could be written as a combination of those. So we've got an nth root going on, right? And we've got those two guys, the nth root of n and the nth root of a constant. Well, we've got an nth root of a constant and we've got an nth root of n. So let's rewrite this. We've got the nth root of 8. And then we've got the nth root of n, nth root of n, and nth root of n, right? So even though this is not in that list, it's made up of 1, 2, 3, 4 things that are in that list. This is the nth root of a constant, which is this guy here, nth root of x. And by theorem 5, we know that that is 1. And then nth root of n, by theorem 5, we know is 1. And so we just say by theorem 5. Be sure to quote it because these are really indeterminate forms. It's not obvious that it's 1, so I want you to quote the theorem there. And so the limit is 1. And so what does that mean? It means this sequence converges, right? When you take a limit and it exists, that means the sequence converges. So these are very useful. So, and you'll get used to seeing them in the homework. They come up in some stuff we're going to do a series quite a bit. And whenever you see them, you don't have to go through the argument. You can just say what the limit is by theorem 5. So yes, I think for most people this is one of their favorite theorems because it helps us avoid a bunch of work.